Hi, thank you. Yes, hi, I'm Phil from Baseten, and as co-founder, I've primarily worked with the infrastructure and performance teams at Baseten from day one. I've come here to talk to you today about how we do things faster, cheaper, and better. Namely, how do we do optimization for inference for production AI? Now, performance optimization for services is a pretty well-trodden path. I think that AI introduces a new set of complexity that makes this problem particularly hairy. I think performance, reliability, and cost matter more today than ever when it comes to your customer's experience. Nobody wants a product that is slow. Nobody wants to use a product that doesn't consistently work. And nobody wants to use a product that is prohibitively expensive. Our goal as a company, and my goal today, is to explain how we can cost-effectively serve open source, fine-tuned, and custom AI models in production with unrivaled speed, scale, and reliability. Now look, there's far too much to cover here in 20 minutes, and so I'm going to try and touch a little bit of everything. But hopefully this piques your interest and gets you curious about how you can apply some of these ideas to any AI initiatives that you're working on today or in the future. I'm going to divide this talk into roughly two parts. The first part is going to be on how can we use different techniques specific to AI workloads to drive better performance. And then the latter half is going to be where the rubber hits the road. How do we take all these performance gains and scale them up to serve thousands or millions of users? So this is the applied performance research. Now, a lot of what I'm going to be talking about is going to be using terms from the LLM world, if you're familiar, but a lot of this also applies to other modalities, such as like image generation, audio generation, structured data, all these good things. Now, so what do we care about here when it comes to performance? Latency, throughput, and quality. Latency is going to be our measure of how our customers, whether they be internal or external, are going to experience our model. Whether that be how many tokens per second we can squeeze out of our model, or how quickly we can generate that first token so the customer immediately feels as though the model is working for them. Then we have throughput. That's going to be our measure of the efficiency of the model. Like how many inputs can we process per instance of our model, or how cost efficient our model is going to be at generating outputs. And finally, we have quality. How do we maintain consistently high quality outputs when optimizing for performance? Faster, cheaper, better. You can probably see how attempting to solve for all three of these constraints is going to yield some sort of conflict. But with careful planning, we can strike the right balance that delivers a result that satisfies both our customer needs without breaking the budget. Now, a lot of this is really in the abstract, and I want to ground everything that I'm saying in a series of real customer stories and examples that illustrate the kinds of problems and solutions that we're working on day to day, and how we've made certain optimization decisions that drive our customer goals. We've had the privilege of working with some really awesome Gen AI companies. In particular, Ryder is doing some amazing work in the enterprise LLM space. We paired up with their team to help improve various benchmarks for their models, showing 60% higher tokens per second, while also reducing the cost by 35%. This is a result of our teams working closely together, both Ryder's engineering team and Baseten's inference platform, as well as our model performance teams and expertise. So when it comes to model performance, we've kind of got three layers to work with here. We've got the hardware layer, the runtime layer, and the model layer. We can think of each of these as levers that we can pull to optimize for different things, like driving latency, throughput, or quality. Now, of course, we're working in a constrained world, and so we're trying to strike the right balance between getting the best latency, throughput, and quality on some particular piece of hardware. And in a world where we're always going to need to balance real-world constraints and maximize economics, eking out every little performance gain that we can is absolutely critical. So what does it look like? I'm just going to go through some of the high leverage optimizations that we can get some performance improvements out of. So to begin with, there's a very obvious candidate. One of them, just picking the right GPU for your problem. This is an obvious price-performance trade-off. We don't want to be spending, we don't want to be getting the best possible hardware for every problem. But given a piece of hardware, how do we maximize utilization? A lot of that is going to be coming from batching and chunking inputs. Also considering using a different model serving runtime that might translate to other performance gains. For example, better cache management, optimized CUDA kernels, but different batching strategies, or even different implementations for algorithms like page attention. If possible, we should always quantize our model. And finally, and somewhat much more sophisticated, we can apply model algorithmic improvements to our model to speed up performance, such as speculative decoding. And again, each of these is just an example of a different lever that you can pull to drive better throughput, latency, and quality. Faster, cheaper, better. So I want to do a quick deep dive into one of the options that we just displayed. That is quantization. It's relatively approachable consideration. Essentially, what we're trying to do is trade off numerical precision for other gains. So essentially, what we're going to do is take high precision numbers, 32-bit, 16-bit numbers, and replace them with smaller ones, like an 8-bit number. For example, FP8 or int8. And what does that actually mean? It means that on the GPU, we're doing lower precision arithmetic. We're also going to be much more memory bandwidth efficient. And so how does that feel in terms of what it gives us? Well, it improves the time to first token. So it's going to be faster. It's going to improve our tokens per second. So that's going to translate to cheaper. But it may reduce the quality of our model. It's faster, it's cheaper. It might be a little bit worse. The performance of this optimization is going to be depend on many different aspects. For example, the model's numerical stability. That is something that we can consider at training time and do quantization-aware training to try and overcome the quality degradation. Certain GPUs, such as H100s, actually have hardware-level optimizations for handling lower precision arithmetic. What this allows us to do is take advantage of all these different things. In particular, H100 handling of FP8 is great because FP8 is going to preserve output quality relative to int8 thanks to FP8's high dynamic range. And this is one of these decisions that maybe in some domain-specific circumstances, the reduced precision actually has a negligible impact on the quality of the outputs. And if that's the case, then it's basically a free lunch. There are so that's like a relatively generic optimization we can do. It can apply to just about any model. And then there are other optimizations that are going to apply specifically leveraging the architectures of specific models. For example, in the LLM world, we have several potential candidates for choices to improve the performance of autoregressive models. Two of those are speculative decoding and Medusa heads. If you're unfamiliar, you can think of them as a smaller model trying to front-run our bigger model by guessing different potential completions to our input ahead of time. And when one of those speculative paths happens to be correct, then we've already done the computation, and we can skip the expensive computation for the larger model. So essentially what we're going to get is speed for free, no quality degradation. You can actually see here the performance gains that we got internally for training Medusa heads on Meta's Llama 3 model. What we see is somewhere between double to maybe a little bit even better than double performance, a bunch of different domains. And yeah, these are great benchmarks. So what's the catch? Well, first of all, it's not simple. It often requires making a good choice for the draft model, or even doing training to create a draft model that is appropriate for your larger model. And the performance gains are pretty hard to predict a priori. So they're very domain dependent. And so it requires some evaluation when you're doing this, whether or not all this additional complexity is worth the effort. But when it does work, it's faster. And when it's faster, generally things you can do cheaper. And when things are cheaper with no quality loss, then it's better. Bringing this back to the real world, our team was able to help our friends at Toby hit their latency-sensitive goals for live multilingual transcription through bringing together a variety of techniques that we've just covered. So that kind of begs the question, how do you, as consumers, actually achieve similar kinds of results? It's like great that we have all these ways to make our models run faster. How do you do it for your workloads? Well, part of what we're doing at Baseten is making otherwise complex technologies accessible through developer-friendly tooling, which we're constantly investing in. For example, our Tensor TRT LLM engine builder. So Tensor TRT LLM is a model inference optimization engine, framework from NVIDIA. We've created an engine builder that generates model inference servers created by Tensor TRT LLM, and support for advanced optimization techniques like quantization and speculative decoding that we just covered. With the engine builder, just about any developer can very simply deploy a foundation model or a custom model that leverages all of the expertise that we've built in-house and get state-of-the-art latency and throughput. It's a better way to make your models run faster and cheaper. So that concludes the model performance half of things. And so now we're thinking, like, how do we take all of this, all these gains out of R&D and scale them up to serve, all your customers? So that's where the distributed infrastructure problems come in. Now, running AI models at scale it poses a pretty challenging set of distributed infrastructure problems. The faster, cheaper, better has tentacles all the way down into the infrastructure layer. And given the cost of running GPUs at scale, we want to definitely auto-scale our workloads to meet the demand of our customers or your customers. But auto-scaling, having a tight auto-scale is going to introduce a new problem, which is around cold starts. These models have 10, 50, 100 gigabytes of weights to load in at runtime. So how do we be responsive to demand in a timely fashion? And given that our customers are just globally distributed, how do we be sure to provide the best experience to ensure all the performance gains experienced by our customers, all while maintaining a reliable user experience and consistent uptime and insulating against GPU capacity issues, not to mention anything to do with compliance or regulatory concerns, or ensuring portability and compatibility with your existing cloud infrastructures. I've only got a few more minutes left, so I'm certainly not going to be able to cover all of that. But what I can speak to is the real experiences of our customers. So we are laser focused on our fundamentals. We work very closely with our customers to ensure the reliability of consistency. For example, RIME, we ensure the reliability and consistency of their P99 latency, which is what their customers are experiencing, the worst case scenario, and we're doing that with 100% uptime over the course of our engagement. So what are some ways that we can think about slicing the infrastructure for AI inference? One way to do it is to look at how the hardware comes together. At the node level, we want to be running things fast. At the cluster level, how do we ensure that we're going to be able to scale to meet unpredictable demand and balance those resources efficiently under load? In the multi-cluster level, how do we bring these wins to our clusters at the global scale, but also our customers' clusters, whether it's a self-hosted or in a hybrid fashion? Given the unique constraints of running ML infrastructure at scale, we've invested heavily in how we allow users to configure auto-scaling policies that match their performance profile, the desired performance profile. As demand comes in and the workloads are going to scale horizontally, load balancing all that demand is another opportunity to optimize both latency and throughput. We actually have some really cool stuff in the works right now around load balancing, and we see this as a non-obvious place of high leverage for achieving cost performance gains with bespoke user-defined load balancing policies. This is cool. Another area of investment that we're spending a lot of time in at Baseten is bringing together all of our expertise and products into your cloud. So basically all of our technology is capable of running entirely within your infrastructure, either as a self-hosted inference cluster or a hybrid cluster where you can use your existing cloud commits or capacity, and when you run out, you can scale into our community cloud. This brings all of our performance gains, both at the model level and at the infrastructure level, into your cloud. One of the huge pain points that we hear around the adoption of AI into a lot of enterprises is like, how do I adhere to all of the compliance and regulatory concerns? Our solution is designed with this in mind. It's designed to short circuit all these compliance, regulatory, and confidentiality issues ahead of time by running entirely within your infrastructure. This solution is applicable for both big and small, new startups operating in regulated industries, or enterprises that are looking for a springboard into adopting AI. Being faster, cheaper, and better requires looking at the problem globally, both at the model level and at the infrastructure level. When you do both of these things together, you can achieve incredible results. Like what I consider to be a great collaborative effort. We were able to work with Bland AI to provide model and distributed infrastructure performance to deliver real-time AI phone calls, all with a latency that makes it feel like a natural phone call. This is Baseten. This is our platform for high-performance AI infrastructure that scales with you. Thanks very much for your time. Please come, and if you have any questions, visit us at booth 1522 just over by NVIDIA.